Excellent, welcome back. So today we'll talk about programming language syntax. We'll talk about tokenizers, parsers. We are going to see several examples of grammar generators or parser generators. I prepared here a couple of examples. First, we are going to cover one example with Python, Lex, and Yak. These are Python packages for the classical tokenizer Lex and parser Yak. We are going to implement them in two different ways. First, we are going to implement a simple calculator that identifies the tokens, and then the parsing rules will directly compute the values of the expressions. This is a simple parser for expressions where everything can be computed on the spot while we are parsing it. Then we are going to see another example of a Python Lex and Yak program that actually will build an abstract syntax tree. So in this abstract syntax tree, when we actually parse expressions or statements, we will need to build nodes in the abstract syntax tree, like binary nodes that contain the operator and the operands. And the reason why we do that is that sometimes while you are parsing, like if you are parsing the statements within a while loop or a loop in general or in a recursive method, you don't have the values of the operands. So the parsing has to be separate from the execution of the program. So in this case, in fact, the result of parsing is in fact an abstract syntax tree that later gets executed. So we are going to see such an example with Python, Lex, and Yak. Then similar examples with the toy parser generator, another package in Python, which actually it's a different type of parser as opposed to Lex and Yak, which are Yak is an LR parser, the TPG is an LL parser. So there are issues of eliminating left recursion, which we'll see why do we have to eliminate left recursion. And more examples. We are going to see how the same program can be actually compiled and written with Antler. Antler is a Purdue written parser generator. Again, there are many different parser generators. You may have heard of Java CC, which is the original Java parser generator, Antler, Lex and Yak, Bison and Flex, and so on. These are all parser generators. They all basically implement in an easier way parsing and writing your own programming language for any kind of domain-specific problem that you may have. So let's return back. Today we are going to talk about syntax and a little bit about semantics of programming languages, and then we are going to implement parser generators from scratch. Basically, we are going to write a Lex, a tokenizer, we are going to write a parser. And we are going to start with simple examples that were already posted on Piazza, and you can run them with Python having installed Lex and Yak with the pip installer. Okay, so programming languages have to be very precise. Basically, any statements that you are writing in a programming language must have their form, syntax, and meaning, semantics, very well defined without ambiguity, because both the programmers and the computers must tell what the program is supposed to do. So the syntax must be very strict and the semantics has to be very exact of what the meaning of the program is, such that the output directly implements the algorithm that you are implementing. For instance, let's take an example. The syntax of Arabic numerals is very well defined. And how do we define the syntax of Arabic numerals? First, we define what a digit is. A digit is either 0 or 1 or 2 or 3 or 4 and up to 9. Then we can define a non-zero digit. A non-zero digit is one of the digits between 1 and 9. And then we can define that a natural number. strictly greater than 0 without preceding zeros is very well defined as a non-zero digit followed by other digits. So it basically starts with a digit that is different than 0, and then it may contain any other number of other digits if the number doesn't start with 0. We wanted to define a very well defined intuition of numbers in basically number systems. So the regular expression, which some of you may be familiar with from CSE303, the theory of computation, is that we can write a regular expression for natural numbers as follows. Non-zero digit followed by any number, that's a clean star, basically any number of the previous pattern. And the previous pattern in our case is digit. So a natural number starts with a non-zero digit and it's followed by any number of other digits. This is a very simple regular expression which basically defines what's the syntax for a natural number. We will see that when we write programming languages, we are actually going to talk about two different ways to implement the different parts of a programming language. First, regular expressions are a simple way which actually can parse the input in linear time with the size of the input using a deterministic finite state automata, DFA, which basically identifies exactly if a token, if a string is an identifier, if a string is a keyword, if a string is a number, and so on. And the reason why we do that is that context-free grammars are more expensive than regular expressions. And we can also write context-free grammars in a simpler way if we define regular expressions first, tokens. So the input to the context-free grammar is not a sequence of characters, but a sequence of keywords, like keywords in a programming language, numbers or tokens that represent numbers, operators, identifiers, and so on. So we'll specify the syntax of programming languages in two parts. First, the tokenizer or the scanner, which identifies words in the stream of characters, and then the context-free grammars, which composes these words into a parse tree. Like, for instance, the fact that we have a block, and in that block we have other statements. Some of those statements are print statements, which use the keywords for printing, like print, parentheses, and all that. And we can write it like in natural languages. The grammars for natural languages are written in the same way. That, for instance, a sentence is a noun phrase followed by a verb phrase. A noun phrase could be a determiner followed by a noun. These are rules of composition of, for instance, English sentences. So we'll start with the most simple part, with the simplest part, which are regular expressions. A regular expression can be one of the following: a single character, the empty string denoted by the empty string symbol epsilon, two regular expressions that get concatenated, like for instance, a name could be a letter followed by a letter, or two regular expressions separated by vertical bar, which has the meaning of disjunction or. So in this example, we see that a name is a letter followed by either a letter or a digit. Again, a regular expression could be also an expression followed by the clean star. The meaning of that is concatenation of 0 or more strings. So, in fact, the definition of identifiers in many programming languages is that an identifier or a name is a letter followed by any number of letters or digits. So, this is the regular expression definition. It's either one character, the empty string, a concatenation of predefined tokens or characters, and then disjunction, either one of the two options, letter or digit, or a regular expression followed by clean star. Now, We learned in CSE303 that theory of computation that the regular expressions are the lowest possible strings that can be detected by a machine, like for instance the deterministic finite automata. But that's not completely correct. There is in fact a large set of families under regular expressions. There are sub-regular languages in which you basically can define languages that use only concatenation and disjunction without the clean star, and then you can see what the clean star may mean. Basically, there are piecewise languages, there are languages which may allow or not disallow the use of expressions and so on. If you are interested in this kind of like sub-regular expression languages, there is a large body of research that I will post, in fact, on Piazza after the class today to see what sub-regular expression languages exist and what are their use. Mainly their use is in machine learning, where you are not given the regular expression, you actually have to learn regular expressions from a set of examples. So regular expressions are used for the definition of many tokens, and here we have the definitions of a bunch of tokens. For instance, a digit is one of the digits from 0 to 9. You can define the syntax of numerical constants with regular expressions. A number is either an integer or a real, and now an integer could be a digit followed by any number of digits. This is a simpler definition of an integer where we can have an integer starting with 0. A real is either an integer followed by an exponent, or a decimal followed by either exponent or epsilon. A decimal is any number of digits followed by either dot digit or digit dot, followed by any number of digits. And now you can see the use of concatenation, clean star, and disjunction in one single regular expression. Because you know that if you write, let's say, just 0 dot or 0.5 should be recognized as a real number, as a decimal number. If you write only 0.5, it should be recognized as a real number. If you write only 0.56, can be recognized as a real number, and so on. And an exponent is just lowercase or uppercase e, followed by either plus or minus or nothing, which means also positive integer. So this is actually the definition that we are also going to use several times for defining tokens for integers or real numbers. It's a very powerful way to define tokens, which represent real numbers. For each one of these, you can actually define a deterministic automata. For instance, you can write a deterministic automata for digit. For either 0 or 1 or 2 up to 9, you have a transition to recognize a digit. If you have disjunction, you have you can write a regular automata for finding this expression. Again, usually the process is that you first write a non-deterministic automata, and then you reduce the non-deterministic automata to the deterministic form of that automata. So regular expressions work very well for defining these tokens. You can define in a regular way using no nested constructs regular expressions. However, we are unable to define nested constructs when we basically have to identify the same number of tokens followed by the same number of tokens. So you cannot write a deterministic automata or a regular expression, for instance, for n zeros followed by n ones. You cannot write it only with the definitions of regular expressions that we had before, which is basically concatenation, single characters, disjunction, or clean star. And there is a proof. If you want to take a look at the proof in the textbook, extension CD. You can also find it easily on Google, on Wikipedia. This proof is very simple, that you cannot write a regular expression that finds if expressions are well defined. mathematical expressions are well defined. That means that every open parenthesis is ended with a close parenthesis. For this kind of grammars, we have to write what is called context-free grammars. Context-free grammars are a definition in this notation, which later we will see that is called the Backus-Naur form, after the inventors of Algol and Fortran. Those are Backus and Naur. And in this notation, we actually can see that every non-terminal, which occurs on the left-hand side of a production rule, is basically the composition of other either non-terminals or terminals. And this can be recursive. So for instance, an expression could be either an ID, a number, or a minus expression with unary minus, or an expression within parentheses, or an expression followed by an operation, followed by an expression. Even these definitions are not always, they don't always define unambiguous grammars. For instance, if in our case the operation is either plus, minus, multiplication, or division, for an expression that has both multiplication and addition, we cannot find, it will parse multiple parse trees because of the fact that it doesn't consider the priority of operators in the definition of the grammar. But even without that, this is a much powerful way to define grammars than the regular expressions. And in fact, there is a proof, there are several proofs. The best algorithms for identifying if strings are following context-free grammars are in cubic time in the size of the string. So they are more expressive, this language, but the computation of this, context-free grammars is much more expensive than regular expressions. So in fact, we have a hierarchy of languages. Context-free languages are way more powerful. They are strictly more powerful than regular expressions. But as I said, regular expressions are faster to recognize input strings. Regular expressions in programming languages are used to create tokens in linear time in the size of the token. And then those are the inputs to context-free languages, which are more powerful for defining grammars for programming languages. So many of you in CSE307 have heard of Chomsky hierarchy, in which we have regular expressions as the type 3 languages. They can be identified with finite automatas or regex. There are programming tools like Lexer, Scanner, Tokenizer that actually can produce in linear time a sequence of tokens from a sequence of characters. Now, next, there are context-free grammars, which, again, with certain subclasses can be solved in linear time, but in the most general case, they are solved in cubic time, n to the power 3. They require a push-down automata, also called a parser, for identifying the parse tree or identifying if a string follows a certain grammar or the rules in a certain grammar. Even these are not enough for defining natural languages. For instance, in English and many other languages, you have also a number agreement and a gender agreement between the nouns and the noun phrase and the verb phrase in a sentence. For instance, if you are in singular third case, you must basically also agree with the verb. He does something instead of he do. And basically, those require what are called context-sensitive languages, which in addition to the parse, the grammar rules, they also have grammar rules that require number agreement. So there is a data flow in parallel with the context flow, with the workflow to parse that specific string. Even those are simpler languages than unrestricted languages, or what a Turing machine basically has as implements as computation. These type 0 and 1 languages are usually too slow for any practical use, for any programming languages use, in fact, because context-sensitive languages are used in natural languages parsing. Type 2 are good for practical use in parsing subclasses of basically context-sensitive context-free languages, especially LL and LR grammars, which are basically implementations of context-free languages for parsing programming languages. In the more general case, the cost of parsing context-free languages is cubic time, and most programming languages don't require that case. Finally, type 3, which are regular expressions, are fast. They require only linear time to recognize tokens, but they are not expressive enough for programming languages. So we are going to use two of these levels. We are going to use regular expressions for finding keywords or words in a program, and also numbers and identifiers and operators and so on. And then we are going to write context-free grammars using parser generators. Sometimes some programming languages also write context-free languages with if statements directly for the input stream of characters, but that is done just for performance optimization, not really for writing parsers. All parsers for programming languages start with two phases: writing regular expressions for tokenizing, and then writing the grammar with the parser generator. So what are context-free grammars? Context-free grammars, first, they are written in what is called the Backus-Naur form. This notation for context-free grammars define what are called productions. These productions are expressions written with this arrow operator, which has on the left-hand side a non-terminal or a variable, which that non-terminal gets parsed into one of these expressions on the left-hand side or on the right-hand side of the production rule. So an expression, for instance, in a language could be an ID, which is a variable, or a number, or a unary minus expression, or an expression within parentheses, or a concatenation of expression, operator, expression, where an operator could be a plus or minus or multiplication or division. So in effect, a context-free grammar consists of a set of terminals. They will not appear on the left-hand side of any production, like for instance, the fact that the input could be a token, like a number. This is already recognized to be complete. We know what's the input. A set of non-terminals, n, a start symbol s, and a set of productions. So basically, the set of productions define every one of the non-terminals. We have an expression is this set of possible expressions. A statement could be another set of statements, and so on, or the composition of the set of statements. Let me just correct this slide so you can see it in a better way in the lecture notes. So John Backus was the inventor of Fortran. He won the ACM Turing Award in 1977. Together with Peter Naur, they invented what is today called was started by Donald Knuth, the BNF form for another programming language called ALGOL. Peter Naur also won the ACM Turing Award in 2005 for the ALGOL language. So context-free grammars use that definition that we saw before with a set of terminals, a set of non-terminals, and then production rules. As you can see in this example, we do not actually use clean star. And the reason for that is that clean star is already subsumed by that language. The clean star and meta parentheses for grouping do not actually change the expressive power of the context-free grammar notation by Backus-Naur, so the BNF form. So for instance, the notation that an ID list is an ID followed by as many occurrences of comma ID, this notation can actually, it's just a shorthand for another non-terminal ID list tail, where the ID list tail could be epsilon or a comma ID followed by ID list tail. So the clean star notation is really not necessary for context-free grammars because context-free grammars already have that complexity, that expressive power for the notation. We can also represent that specific expression, the first one, in a different left recursive version. An ID list is an ID, or an ID list is an ID list followed by comma followed by ID, which allows us to have as many ID list comma IDs in front of the last ID. So that specific original production that uses the clean star is really not necessary. The clean star can be easily transformed into just recursive rules. Okay. Okay. Regular expressions can also be represented in the BNF notation. Again, we basically can write every clean star as a recursive rule. So we start with A star, and we basically get any number of A's is an A followed by any number of A's or epsilon. So now A star has two production rules, or one production rule that uses disjunction for defining any number of A's. So now concatenation can also be expressed by a regular expression, and if we have the other clean stars, they can also be represented through multiple rules that use recursion. So in fact, B followed by any number of A's followed by B any number of times can be represented as a new non-terminal S, which is B followed by A's followed by B followed by all recursively also the non-terminal S or epsilon. So now this entire clean star can be represented by BNF production rule. And finally, if we want for the entire regular expression to represent it as a non-terminal, we can say that it's basically any number of A's followed by S. And now we have production rules that represent that specific regular expression that we had above. And in fact, this is useful for also drawing or finding the deterministic finite automata for regular expressions, because we can label sub-automatas within the outer automata for regular expressions. Before we actually do parsing, let's actually learn the terms that we are going to use for parsing, and also how do we actually build these terms. So a context-free grammar shows how to generate a syntactically valid string of terminals that is represented by that grammar. So we start with the start symbol. Let's assume that some S is the start symbol. We can choose a production rule with that start symbol on the left-hand side, and we can replace that start symbol with the right-hand side of that production. So we basically start with S in our previous example, and or G, and we replace G with AS and S. Okay. So now we can choose any non-terminal A from the resulting string, and we choose a production rule P with A on the left-hand side, and we replace that A with the right hand side of P. So in the previous example, we can choose, let's say, S, and we replace S by one of the production rules for S. We repeat this process until no more non-terminals remain. So basically, we will unfold every one of the non-terminals until we have only tokens. So in fact, context-free grammars can be used not only for recognizing if strings follow the grammar, but actually for producing strings that can actually that are recognized by the grammar. So you can think of, for instance, using a natural language grammar to generate sentences that are grammatically correct. Now, if you choose, so the algorithm that we talked about above does not make any assumption on which non-terminal we are choosing from the string. So in the previous example, we can either choose AS or you can choose S. But the algorithm itself makes no requirement of which one of the non-terminal is chosen. Then there are strategies. If we always choose the rightmost derivation, the rightmost non-terminal, or we work on the rightmost part of the current string that is generated, that is called the rightmost derivation. Rightmost derivation chooses at each step to replace the rightmost non-terminal with the right-hand side of some production that matches that non-terminal. There are many other ways to actually do these derivations. In fact, the LL parsers use the other way, use what is called the leftmost derivation, which basically chooses on the left-hand side the non-terminals to solve them. So let's take an example. Let's consider the grammar that we discussed earlier, that an expression is an ID or a number or a minus expression or an expression within parentheses or an expression operator expression where an operator is either plus or minus or multiplication or division. And we can try to use our grammar for expressions to generate the string slope multiplied with x plus intercept. So as I said, we always start with the root, with the starting symbol. Our starting symbol is expression. For expression, we can choose any one of these disjuncts. So in our case, we can choose expression operator expression. So we choose that, and now we can do rightmost derivation. Expression is also non-terminal. So we can basically resolve it either by using one of the using one of these right-hand sides. In this case, we choose ID. ID is basically a token, so can be intercept, but we can leave it as ID. So it's expression plus ID. Now the expression operator ID. The rightmost non-terminal is operator. Again, we can choose any one of the operators. Let's choose plus. Now the rightmost non-terminal is again expression, which we can use the production rule that says expression is expression operator expression. The rightmost non-terminal is the second expression, which could be again solved to ID. Operator is now the rightmost non-terminal. We can solve it to multiplication. And expression, we can solve it to ID. At this point, we actually do not have any more non-terminals. So the tokenizer can actually give us that slope is the ID, x is the ID, and intercept is the ID. So this symbol that we see with arrow, the double arrow, it's a metal symbol that we pronounce as derives. This is called a derivation. From the root symbol, we can basically get to an expression that only contains tokens. This series of replacement operations that shows how to derive a string of terminals from the start symbol is called a derivation. Each string of symbols along the way, so each one of these, like expression plus ID, is called a derivation. It's called a sentential form. And the final sentential form, consisting only of terminals, is called the yield of the derivation. So we can represent a derivation graphically as a parse tree. Like for instance, the previous example, we can actually start from the first derivation. An expression is an expression operator expression, and that would be a node in our parse tree. We have the root as the starting symbol, and then we have the leaves are the yields of our derivation. Each node has the children of a production. So the first production that we use transformed expression into expression operator expression, and then expression was a number, which could be a number 3, operation could be a plus, and so on. So for instance, if we build a parse tree for the expression that gets derived 3 plus 4 multiplied with 5, we can actually build this parse tree. We are losing a bit of information. That bit is the fact that we always apply rightmost derivation. We basically, the canonical derivation is the fact that we start from the right hand side to solve non-terminals. However, the problem with that grammar that we saw before is that the grammar is ambiguous. It does not consider the priority of operators. So for instance, the expression 3 plus 4 multiplied with 5 can be parsed in two ways, as 3 plus 4 multiplied with 5, which is the intended meaning because multiplication has higher priority than addition, and one that is 3 plus 4 everything multiplied with 5, which is another parse tree which is allowed by the same grammar, because the grammar did not make any assumption of the priority of operators. So this specific grammar that we saw before is ambiguous, and that is not a good grammar for programming languages, because at the beginning of the class today we said that programming languages grammars must be unambiguous. If you write an expression, that expression has a single meaning. In this case, we can see that we can basically gather the value of that expression, if that expression is computed, is different depending on how we parse that expression. 3 plus 4 multiplied with 5 is 23. 3 plus 4 everything multiplied with 5 is 35, because it's 7 multiplied with 5. So the two parse trees are, having two parse trees is not correct. We should have a single parse tree for any input string to the grammar. So we can write a better version of of our expression grammar that also introduces precedence and associativity. Also, associativity is important. We will see in the case of division that if we have, let's say, 10 divided by 2 divided by 2 should not be 10 divided by 2 divided by 2, which is 1. It should not be 10. It should be 10 divided by 2, which is 5, divided by 2, which is 2.5. So for that, we need to actually implement both precedence and associativity. So let's start with this grammar that actually defines both precedence and associativity. So expression is a term, or is an expression, add operation, another term. So now we basically implement the fact that addition has lower priority than multiplication, because multiplication will be solved by another non-terminal term. A term is a factor, or is a term followed by multiplication operation followed by factor, where factor is ID, number, which are tokens, minus factor recursively, unary minus, or an expression within parentheses. And addition operation is plus and minus, or minus, and multiplication is multiplication and division. So now if we give a string, like for instance 3 plus 4 multiplied with 5, there is a single parse tree, a single derivation for that specific string. An expression is an expression add operation term, the only way that we can actually parse that string from the root symbol expression. An expression could be a term, could be a factor, which is the number 3. The add operator is plus. The term is a term multiplied with a factor, The term is a factor, which is a number 4. Multiplication is multiplication, operator, and factor is the number 5. There is only one parse tree for such arithmetical operations, and that's exactly what we want. And here we have another example, and the fact that our grammar is also left associative. Basically, any additional addition operation, like for instance 10 minus 4 minus 3, will be computed on the left hand side is 10 minus 4, which is 6, and the result of that subtraction minus 3, which will give us the result 3, instead of 10 minus the result of 3 minus 4, 4 minus 3, which is 10 minus 1, which is 9. There is a single parse tree for that specific grammar that we had before, even for left associativity. And also this is important for division. So our grammar is both left associative for all of the operators and has higher priority for addition and subtraction, has lower priority for addition and subtraction versus multiplication and division. Before we continue with basically how are these implemented in programming languages, let's see if there are any questions in the chat. So please ask any questions you may have about what we discussed up to now. What we discussed up to now may actually overlap with what you already learned from CSE303 theory of computation. But now we are actually going to do it in programming languages. In 303 you have not written a programming language from scratch. You have not actually learned how to use a parser generator to write your own programming language. If you want to develop a new Python or Ruby or JavaScript or anything that you want to do, this is what we are going to do in this class. So up to now we discussed topics that you may be familiar with from 303. The fact that regular expressions are basically the basis of detecting with deterministic finite automata strings that may identify tokens or numbers in programming languages, and that you can combine these strings using a parse tree into an abstract syntax tree for a program to actually execute in order the statements of that program. So let's see if there are any questions in the chat. Looks like we have no questions, so let's continue with programming languages. So, one second. So the first basically process, the first part of the program that actually takes the input sequence of characters is called a scanner or tokenizer or lexer. And together with the parser, which is the next part that we are going to talk about, they are responsible for discovering the syntactic structure of a program, also called the syntactic analysis of the program. The scanner or lexer, this first part, is responsible for tokenizing the source code, basically identifying keywords, names or IDs, numbers in a program. The output of the tokenizer or the scanner will be used in the next phase, which is parsing, for identifying the structure of the program. Also, the scanner removes comments, because basically if you have any commented line, it will skip everything up to the end of the line. The scanning is also considered together with other programming languages tools like preprocessor to remove comments, deal with pragmas like significant comments that may be collected for documentation purposes, saving the text of identifiers or variables, constructing the symbol table for all of the variables in the program, identifying and saving numbers or strings identified during compilation from the program, like intern strings. It should also save the location of the source code, like the file the line number and the column number for error messages or for debugging. The scanner turns the program into a string of tokens or a list of tokens. It basically matches regular expressions to the program in order from left to right, from the beginning of the program to the end of the program, and creates a list of tokens. There are two syntaxes for regular expressions that we are using. First is the Perl style regular expressions that are using clean star, but we may also write regular expressions into the BNF form or the extended Backus-Naur form, which is this notation that basically we define non-terminals on the left-hand side and terminals on the right-hand side. In the case of regular expressions, basically we have tokens on the left-hand side and regular expressions of characters on the right-hand side. Scanners or tokenizers can be built in three ways. We can write and generate a finite automata for the regular expression. We are going to do that by hand, or using scanner code, usually realized with if or switch case statements. Basically, if this is the current character, what is expected next? Or if it's nothing expected next, then identify the token. Usually they are using some look ahead, like they are looking at the next character to identify if maybe it's a white space, and then or any other type, or an operator that is not expecting the current token to generate the current token and then continue scanning. Or the third way to implement scanners is called the table-driven DFA. We are going to see an example for that later this lecture when we talk about context-free grammars. Basically, based on what is the token, the current token that is identified and what is the current character in the input stream, we are told what is exactly the production rule that we should use. So it uniquely identifies the production rule from the current token and the current input string or the current input character. Writing or generating finite automatas by hand actually yields the fastest, most compact code by doing a lot of specific special purpose things. Although generating automatically scanners comes very close to that. Many programming languages were implemented this way. They were first defined, like you will find in user manuals, using parser generators and tokenizers using regular expressions and grammars or context-free grammars. But then, in order to make the parser very, very optimized, it was written by hand. It was written with if statements that consider every character and what is the next possible character that can appear in the token. If you look at C parsers or Java parsers, you will see that they are implemented by hand using if statements, and some are implemented using grammar generators or parser generators. So first, let's do it by hand. We want to construct a non-deterministic finite automata equivalent to a regular expression. And there are multiple cases. The base case is that we identify one character. The corresponding NFA for one character is that from the current state, with that one character, we get to a final state. Then we have concatenation. Let's assume that we already built a non-deterministic finite automata for the regular expression A. We already have a non-deterministic finite automata for the regular expression B. If we want to identify A, B, basically the concatenation A followed by B, the concatenation of A followed by B, then we can just unite the two non-deterministic finite automatas, use the final state for A to start the regular expression for B. So it will be basically A followed by B. Similarly, alternation can be implemented if we have again deterministic finite automata for A and for B. If we want to implement a non-deterministic finite automata for A or B, we can actually, from a start state, we can either go to the automata that detects A, or we can go with an empty transition for the automata that detects B. At this point, by automata, I mean not non-deterministic automata, because here we non-deterministically go either to A or to B. So now we get one non-deterministic automata that detects A or B. More complex is the clean star, but not very complex. Basically, if you learn how to represent clean star, you can actually now represent any regular expression into NFA. So let's assume that we want to represent A star. And we already have a finite automata for A. Then we can represent A star as follows. From the input state, we can get to the end state with epsilon. That is the case that the non-deterministic automata application of A does not actually have any A. So we can get with an empty transition to the end, or we can get with an empty transition to a transition that requires the execution of at least one A, but then we can have as many applications of A as possible. Or we go to the end state. So this means no A's, or one A, or one A followed by another A, or any number of A's. And now if we need, for instance, to represent, as an example, a regular expression for detecting decimal numbers, that is any number of digits followed by dot digit followed by digit dot followed by any number of digits, we can actually represent this as a non-deterministic automata. So first, for every one character, we have a simple deterministic automata. We have from the start symbol, with one dot, we get to the end symbol that recognizes that dot. Similarly, from the start symbol with one digit, we can get to a state that represents that digit. If we have concatenation, and that is dot digit or digit dot, we can represent them as two non-deterministic automatas. From start symbol, we can recognize dot, get to a state. From that state, we can recognize digit and get to a final state that recognizes dot digit. And similarly, we can write the automata for digit dot. And now, if we want to represent the disjunction within, it's either dot digit or digit dot. We can do it with two epsilon transitions from the start state to either dot digit or digit dot. Now, we want to represent digit star, and digit star we can represent with this start phase that from start we can get to final, or to a state that requires to implement digit at least once. And we can represent everything digit star followed by either dot digit or digit dot followed by digit star by one single non-deterministic automata. At this point, we will label every state with a unique identifier. So you see we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we basically build incrementally the non-deterministic automata from the regular expression. Now we want to find a deterministic automata. We basically non-deterministic automatas, in order to guess what is the right transition, we have to take every single possible epsilon transition from the current state. So any practical implementation of an NFA would really require to explore all the possible transitions concurrently, or we need to backtrack to follow other transitions. Instead, we will actually transform the NFA into the DFA. So we start with the state that the state of the DFA after reading any input will be the set of possible states that the NFA may reach for that same input. So, for example, initially, before it consumes any input, the NFA may be in state 1, or with an epsilon transition, it can get, in our example, to state 2, or with an epsilon transition it could get to state 4, or with an epsilon transition it could get to state 5 or 8. So really, the possible states in which at the beginning, before consuming any single input, our NFA could be is 1, 2, 4, 5, or 8. Now, let's assume that we are basically representing a DFA. A DFA would have a single state, let's call it state A, that corresponds to our NFA states 1, 2, 4, 5, and 8. Now let's assume that the next input that we are getting is D. What are the possible states that we can get if we actually, the input to our NFA is D? So, from either of the input states, 1, 2, 4, 5, or 8, with a D we can get to state 3. Also with a D we can get from state 8 to state 9. So from state 3 with epsilon transitions we can get to 4, 5, or 8 themselves. So with a D we basically can get to states 3, 8, and 9. To states 3 or 9. But if there are no other transitions from this input to any of the states, we basically can get also from state 3 to 4, 5, or 8. Therefore, we create a new DFA state, which is basically with a D, with a deterministic automata from the state A, we can get to either one of the states in the non-deterministic 1, 2, 3, 4, 5, 8, and 9. Similarly to that, let's see with a dot. Initially, we could have been in state 1, 2, 4, 5, and 8. Now, if we have an input 1, a dot, that dot cannot be consumed by a digit, so we can get with dot to state 6. So really, the next possible state, there are no other transitions for that input from any of the states in state A. Therefore, there are no other epsilon transitions of state 6. Therefore, we have a single state in the non-deterministic automata that corresponds to the state C in the deterministic automata. And we continue this process until we find all the possible states in the DFA and the transitions in the DFA. And this is a finite process. Why do you think this is a finite process and we can always get from an NFA to a corresponding DFA? Let's see if you can actually guess. Why can we always do that? From an NFA we can always get to a DFA. Any idea? So I give you a hint. The power set of the possible states that we have in the NFA is finite. It's the set of all the subset of those states. So we basically cannot, the number of possible states that we can have in the DFA is finite. Also, the number of the input symbols in our possible tokens that we basically, or characters that we can get in the language is finite, that we can recognize from that specific. We take all the characters that we have in the regular expression that are characters, and we can basically get a finite number of states with a finite number of transitions. So we can always build the DFA of the NFA and for any regular expression. So in our case, to recognize digits followed by dots and any number of digits followed by digit dot or dot digit followed by any number of digits has one equivalent DFA built out of the NFA. So we see here, for instance, that from the original states or the start state, which were 1, 2, 4, 5, and 8 in the NFA, with a digit we get to a new state, or with a dot we get to a new state. So now it's expecting that after dot we can only have a digit. That can be a finite state, or we can have other digits, and that will take us to another finite state that has also a self-transition. So we can get from that state to itself with as many possible digits. That we recognize dot any number of digits. Or the other way is to actually identify a digit followed by any number of digits, followed by the decimal dot. We can get to a finite state, and then followed by any number of digits. And now we have two possible states, one in which we require that we have exactly one digit, or one in which we have as many possible digits as possible. Now this is not yet simplified completely. We only basically did the first phase, that we found a DFA. In most cases this is actually enough, because we have a DFA. In finite time or in linear time with the input, we can identify if the input, with that input we can get to a final state, or we cannot consume the input. But usually this is also followed by a simplification phase. That simplification phase will try to unify any of the possible states of the DFA. So we can consider, for instance, A and D together, A and B together, and then to have a loop from that state AB to itself with a digit. But this is not really necessary. We can actually always continue with this unsimplified DFA, and that's fine. So we said earlier that there are three different ways to construct scanners. One is to write and generate such a finite automata. The second one is to write a scanner code you realize with if statements. So we are going to do the second case too. So suppose that we are building such an ad hoc handwritten scanner for a calculator. And this is the grammar basically that we are following, or the regular expressions that we are following for each one of the tokens. Colon equal is a token, plus is a token, minus, multiplication, division, open parentheses, close parentheses are tokens. An ID could be a letter followed by any number of letters and digits. A number is a digit followed by any number of digits, or any number of digits followed by dot digit or digit dot, followed by any number of digits. And the comment starts, it's either a paragraph comment, basically it starts with /* any non-star or star non/ characters. Basically we do not have the end. You can have as many characters as possible until we reach * or a new line comment, or a line comment. Basically two / followed by any non-new line character as many times as possible, followed by new line character. And the question is, how do we actually build a scanner with if statements for this grammar? So we read the characters one by one with a look ahead of 1. First, we skip any white spaces. We can write an if statement that if it's white space, the current character, it just reads the next character. If the current character is either open parentheses, close parentheses, plus, minus, or multiplication, we actually found a token. These are unit tokens that once identified should be returned. We should return the token. This is open parentheses, close parentheses, plus, minus, and multiplication. If the current character is colon, then we read the next character. If it's equal, then we return the assignment token. If it's just colon by itself, we announce an error, because there is no token that contains colon followed by not equal. If the current character is /, now this could be division or either the beginning of a line comment or the beginning of a paragraph comment. So we pick at the next character if it's multiplication, if it's star, or if it's /, then we have to basically identify the comment. So we read all the additional characters until we reach end of paragraph comment, or we see new line in the case of line comment. We ignore that these are not tokens, so we jump back to the beginning of the code. Skip all the white spaces and again tokenize. Else we return division because we identified /, but it's not followed by star or /. If the current character is dot, then we read the next character. If it's a digit, then we know that it is a number. So we read any additional digits. And we return the number after we read all the digits. Else, if it's just dot, our grammar has only digit, period, before in the use of number. So our grammar does not have any other tokens that need period. So if it's period by itself, period should always be followed by a digit. We cannot actually have other tokens. So if it's not a digit, we announce an error. If the current character is a digit, then we have to read all the additional digits and at most one decimal point. And once we read that, we return the number. If the current character is a letter, it could be an identifier, so we read the additional letters and digits. We check if those are the read and write keywords, because those are specific keywords. If they are, we return the tokens. Otherwise, we return that is an ID token. Otherwise, if it's just a single, if it's not a letter, if it's not a dot, if it's not a digit, and so on, we announce an error that is a token that we don't know. So basically what we are doing, we are writing a program with if statements that implements this DFA, this pictorial representation of that grammar that we saw before. So we basically implement ad hoc by using if statements a grammar that identifies tokens in a deterministic way in a linear time with the number of characters in the token. So you can see in this pictorial representation of the scanner for calculator that we really do that. Any white spaces are skipped and we are still in the start state. If we identify /, we could be in division, but we always recognize tokens up to the last token, last character that cannot be recognized. So there is an implicit rule in tokenizers that do not stop until you cannot consume the next character. So we are not in the final state unless we cannot consume the next character is not /, to be a line comment, or is not a star to be a paragraph comment. In that case, we can basically recognize paragraph comments and return to the start state the moment that we basically ignore the comment. And the same happens for line comments, where we basically ignore all the non-new line characters and we return to the start state after we have a new line character. And the same thing we see for other tokens. Tokens that are a single character are returned, basically we return left parentheses, right parentheses, plus, minus, star, and so on. Colon must be followed by equal, in which case we have an assigned token, or if it's not followed by equal, we actually have an error in the tokenizer. The tokenizer announces an error. A digit can be, a number can either start with a dot or can start with a digit, in which case we have to consume all the possible digits, followed by dot, period, followed by other digits. Or we consume all the digits after the decimal period. Finally, letters could be identified. Basically, the letter can start an identifier or a keyword. So we run this machine over and over again, and we get one token after another. And the general rule is that we always take the longest possible token for the input. So for instance, if the string in the input is foo bar, we actually want to parse all of it. We don't want to stop like the regular expression after f or after foo. Okay, so not after f, not foo, not foob. We return the entire string that can be parsed, the entire token that can be parsed. Similarly, for instance, for 3.14159, it's an approximation of pi. It's a real constant. We don't stop after 3 announcing that we found an int, and then we recognize a real number that starts with period. No, we actually parse it the entire thing at once, and we return that this is a real constant, 3.14159. So the rule about the longest possible digit token means that you only return when the next character cannot be used to continue the current token. The next character will generally need to be saved for the next token. Even if you read it and you cannot use it, you announce the current token and you backtrack and you basically give the previous character as the input, the next input to the scanner. In some cases, you may actually need to pick at more than one character of look ahead. Like for instance, in Pascal, you cannot stop after you identify period that, oh, the next digit is not a digit. The next character is not a digit, because you may actually have a range. Ranges in Pascal were using 2 periods, like 3 period or ... 5. So the tokenizer would have to look at not only one digit ahead, like for instance, the one character ahead, but after this period you will have to check, oh, it may be period and then a digit. So then you have basically not a real number, but really a range that must be identified by the scanner. But the number of tokens that you have in the look ahead is basically, you may have multiple characters on the transition from a certain state. So writing pure DFAs is very useful. It's actually a very useful programming technique. C is actually, many parsers for C or C-lang are actually written manually by developers, by programmers like you. But you may also find other programming languages that really require that you write Lex or basically a table generated DFA that will generate the deterministic finite automata from your regular expression. So it will compile your regular expressions into this kind of if statements that we saw before. And in fact, in our class, we are also going to talk today about Lex, which is a standard tool for tokenizing or scanning input strings into tokens. It's also very useful to write these regular expressions in parse style regular expressions. And here, just to again summarize regular expressions, concatenation can be obtained by just enumerating the tokens like A, B, C, D, means the tokenization, the concatenation of A, B, C, and D. Grouping is done with parentheses. We can basically specify alternatives like either B or C. So this is a grammar that recognizes A, B, D or A, C, D. Or clean star. Star means 0 or multiple any number of times, A followed by any number of B or C's, strings that may be actually out of B's and C's in any possible order, followed by the terminal D. And we have multiple operators in this clean star group. Question mark stands for 0 or 1. Star means 0 to infinity, and 1 means 1 to infinity. Either one of these can actually be represented, all of them can be represented in BNF without the use of these operators, because we can use recursion. If we want to have the disjunction of characters like B or C, we can put it within brackets, and moreover they are used for ranges. We can have either a lowercase, an uppercase, a digit or underscore. Dot matches any character, /A stands for alphabetical, /D stands for numeric, /W stands for word, and then we have uppercase W, which stands for a non-word character like alphanumerical, and /S stands for space. Usually you learn regular expressions by examples. So basically you're given a problem and you look at examples like our regular expressions for real numbers, which can start with any number of digits followed by either dot digit or digit dot followed by any number of digits. And then you write it in the regular style and use it in any programming language. Perl was the one that introduced regular expressions, but since then we have them in Java, C#, Objective-C, Python, and so on. Okay, so again, let's take a short break for taking questions. We actually finished with tokenizing or regular expressions, and we are going to go into parsing. So the tokenizer or the scanner recognizes tokens and passes them as input to the parser. The parser will basically take these inputs and assemble them into a syntax tree. And it will pass that syntax tree, perhaps one subroutine at a time, to the later phases of the compiler. This is called syntax directory translation. The next phase may be semantic analysis. Basically, in this syntax tree, we are looking for the meaning of the statements, and we are going to generate another intermediate form, which is usually called the abstract syntax tree. It's a syntax tree that has eliminated already the special symbols. We basically don't need parentheses, semicolon anymore, and so on. And this can be directly executed, and we are actually going to directly execute it as our project in this class. So most parsing tools are using what is called the context-free grammar, or CFG. It turns out that the best algorithms for parsing any CFG runs in cubic time, O(n) cube. And these are the best algorithms for CFG recognition. Early algorithm or Koke-Younger Kasami algorithm, CYK algorithm. And it's clearly unacceptable for a parser in a compiler. It's too slow for, let's say that we have a program with 100 tokens. This is a small program in a programming language. If you write a program at the end of CSE114, Computer Science 1, of let's say 100 lines of code, no, even like 30 lines of code, in each line you have an average of at least 3, if not more, tokens. In an assignment of a constant to a variable, or in a declaration of a variable, you have 3 tokens or 4 tokens. So it's clearly unacceptable for parsers. If you multiply 100 with itself, you basically get 10 to the power 6, which is 1 million cycles. This is only for parsing the input of a small program. This is clearly unacceptable. So fortunately, there are large classes of grammars for which we can build better parsers that can run in linear time. And the two most important classes are called LL, which stands for left to right, leftmost derivation. Leftmost derivation means that we'll work on the left-hand side of the tree. If you remember earlier today, we talked about derivations, and we talked about canonical derivation, which is rightmost derivation. We take the non-terminals at the end or at the right-hand side of the tree. In leftmost derivation, we take the non-terminals on the left-hand side of the tree. So LL stands for leftmost derivation, or left to right leftmost derivation. LR stands for left to right rightmost derivation. We work on the right hand side of the tree to build the parse tree. Also, we will see that LR parsers will start from the root symbol, and will actually, from the root symbol, will apply production rules to build the tree. So we start from the top of the tree and we build down the parse tree. LR parsers are called bottom-up parsers or shift-reduced parsers. They build subtrees and then we decompose them in higher and higher trees until we get to the root symbol for this parse tree. So we are going to introduce first the idea or the intuition of both parsers, LL parsers and LR parsers, to the same example. And we'll see how this works on the two types of parsers, and we are going then to implement these parsers. We are going to implement LL parser using table-driven parsing in linear time, based on what is the input symbol, like the current non-terminal and the token that we get from the tokenizer, what is the production rule that we have to use exactly. So let's see if there are any questions in the chat. And then we are going to continue with top-down parsing and bottom-up parsing, LL and LR parsers. Any questions up to now? Okay, so if there are no questions, let's save the first recording. We are going now for over an hour or an hour and a half. Let's save it, and then we are going to see if we can actually cover the second part of parsing also today, or we are going to do it maybe next time. Let's see. So, just to give you an idea, before I'm stopping the recording, how is this done in Ply, which is Lex and Yak implemented in Python? We are going to generate the tokens. The tokens are basically regular expressions as we saw them earlier. You see they start as strings in Python, R, regular expression. And then we are recognizing that, for instance, a name starts with lowercase letter or underscore or uppercase letters, and then they have as many symbols as possible, which may contain lowercase, uppercase letters or digits or underscore. Numbers are, in this case, I have a very simple integers that contain at least one digit, but may contain as many digits as possible, and I'm parsing them into a value that is actually the value of that integer, the cast of that integer, a string to an integer. And then we have a few more characters. New line is a token, and for any other tokens we should generate an error and we should skip the token. So now basically Lex will actually lexicalize the entire code, and if we took a look at the end in another example, we'll see that we take the input code, which can be a program that we read from the input stream, as we will do in the homework, and you also read with the same probably open file the inputs for the current homework. And every token can be printed, or we can actually print the type of the token and the value of the token. And then that will be the input that we are passing to the parser. Yak, which is the parser in our case, is defined in a different way. It basically identifies in the parse tree each non-terminal and the production rule for that specific non-terminal. And we are going to see how that can be done in two different ways next time. I already posted in Piazza an example. So let's, for the moment, save the current lecture, and then we'll take questions.